So in this lecture we will deal with the quadrilateral element again, and we will try to start from the beginning and we will reach till the end. We will try to do that in this lecture. So let us draw a quadrilateral element, and we know some of the details of this. So, or rather, let us do this. Oh, yeah. So okay, and then we have the local coordinates -1 because this axis is zeta, this axis is eta. So here the value is -1 -1, and then we have, so the value of eta is -1 1 -1. This is 1 comma 1, and this is, so zeta value is -1, eta value is 1. So these are the coordinate system, and we have node numbers 1, 2, 3, and 4. The shape functions I can write as 1 by 4 into, and this we know from our Lagrangian formulation, 1 plus zeta I into 1 plus eta I. So if you put the value of zeta I and eta i's, you will get the 4 shape functions. Okay, we have our shape functions, and then we can define our displacement as n into D matrix, where D is the nodal values of the displacement. So what is D? D is simply u1 v1, u2 v2, u3 v3, u4 v4. This is that. And what is n? N matrix is n1 0, n2 0, n3 0, n4 0, 0 and 1, 0 and 2, 0 and 3, and 0 and 4. So if I have to write the value of u, then it will be n matrix, which is this. So n1 0, n2 0, n3 0, n4 0, and 0 and 2, 0 and, sorry, n1 and 2 and 3 and n4 into u1 v1, u2 v2, u3 v3, u4 and v4. So this is actually, so u is actually u and v, or I can also write it as u is actually ux and uy, which you can represent as u and v, and that will be the value at any point in the element. This is the interpolation, right? So at any point in the element, the value of u will be n1 u1, n2 u2, n3 u3, and n4 u4, right? And then v will be n1 into v1, n2 v2, n3 v3, and n4 v4. So this is how we get the values of the displacement. Okay, so this we can simply write as u is equal to n into D matrix, right? We can also write coordinates x1, sorry, we can write coordinates x and y's as n matrix into the local coordinate values. So x1 y1, x2 y2, x3 y3, and x4 y4. and you simply can assume it. So just put this, so you will have n1 into x1, n2 x2, n3 x3, n4 x4. That will be the value of x at any point in the element. Okay, so this is how we can define our coordinate system, and these are the signature of isoparametric formulation or isoparametric parametric element. Okay, so now if we have a function f and we want to find out the partial derivative of this function with respect to the local coordinate system, so del f by del zeta and del f by del eta, then that simply will be del f by del x into del x by del zeta plus del f by del y into del y by del zeta, and then we have del f by del y del f by del x and del x by del eta plus del f by del y and del y by del eta, right? And this we can write as Jacobian into the column matrix del f by del x and del f by del y. So what is happening? We want to find out the partial derivative with respect to local coordinate system. We get a Jacobian and the relation of the partial derivative with the global coordinate system. So Jacobian describes this relationship. What is Jacobian in this case? So in this case, you look at this formulation and you see what Jacobian is. So Jacobian, so let us not put equal sign. So Jacobian is simply del x by del zeta, del y by del zeta, del x by del eta, and del y by del eta. Isn't it? So you multiply this with this, and you will get this. Okay, so you see this will be del x by del zeta into del f by del x, that is first term, plus this into that second term, and then you want to find out this term, so you multiply this with this. So del f by del x into del x by del y and del f by del y, del y by del eta into del f by del y. So you get this term and you get this term, and that's how you get it. So this is the Jacobian matrix. Okay. So Jacobian matrix has 4 terms. Eventually there are 4 terms, and we can denote these 4 terms as J is equal to J11, J12, J21 and J22, right? So what is J11? J11 is del x by del zeta, J12 del y by del zeta, J21 del x by del y, no, it is eta, so del x by del eta, and this is del y by del eta. Okay, so now we have Jacobian, and if we have to reverse the relationship, if we want to find out the relationship between the partial of any function with respect to global coordinate system in terms of partials of that same function with respect to local coordinate system, then we can write it as del f by del x and del f by del y is equal to the inverse of Jacobian into del f by del zeta and del f by del eta, right? And we can write the inverse of J as 1 by determinant of J into J22 minus J12 minus J21 J11, right? So this you can simply verify by doing simple matrix operation, and this will come down here and this will come down there. So I'm just changing J inverse term to this value. Okay, if I have to find out the relation of the area dx by dy, then that relation is simply given by determinant of the Jacobian matrix into d zeta d eta, and this we have seen, right? This we have seen before, and in 3 dimension of course it will become d psi also will be there. So dx dy dz will be determinant of Jacobian, d zeta d eta and d psi. Okay, so that is our relationship, and then we do then let us find out the strain value. So far not much complication. Also now there will be not so much problem. So the strain matrix in 2 dimension for the quadrilateral element will simply have components like epsilon xx, epsilon yy, and gamma xy, right? And what will be these? So these will be del u by del x and del v by del y, and we will have del u by del x, sorry, del u by del y plus del v by del x, right? This is how we define the strain, if you remember the strain formulation, right? So we are just shrinking the general formula, which is del ui by del xj plus del uj by del xi. We're simply doing that. Okay, so now we have strain value, and in order to find out this strain matrix, we need to find out the partial derivative of the function u. So we need to find out del u by del x, and we need to find out del u by del y. We need to find out del v by del x, and we need to find out del v by del y, right? Now remember this general formulation. For any function this is valid. So instead of f, we have to put the variable which is displacement. So we can find out del u by del x and del u by del y as, so this will be equal to J inverse, which is 1 by determinant of the Jacobian, into J22 minus J12 minus J21 J11 into del u by del zeta and del u by del eta, right? Similarly, we can do the same thing for del v by del x and del v by del y. We will have similar equation for that. Okay. Now, can we define our strain matrix in a different way? So let us define our strain matrix as some matrix A into del u by del epsilon, sorry, del zeta, del u by del eta, del v by del zeta, and del v by del eta. Okay, because we have to do this, because if you look here, we need to find out these three terms, but these three terms has to be described in the relation with the local parameter variable, because we are doing everything in the local coordinate system. So we need to have a relation with the partial derivative in the local coordinate system with the global coordinate system, and that relationship will be described by the matrix A. And what is this matrix? This matrix will be some special arrangement of this Jacobian matrix, right? You see what we have to do. Let us go back. What we have to do is, in order to find out the first term, we have to find out del u by del x, right? Del u by del x has to be found out in terms of del u by del zeta, right? And del u by del eta. So what will be del u by del x? Del u by del x will be 1 by determinant of j, j22 into this plus minus j12 into that, right? So del u by del x will be a function of del u by del zeta as well as del u by del eta, and this is why we have these four partial derivative terms here. And the matrix A. What is this A matrix? The A matrix, or I can write strain as 1 by determinant of j, and then I have this matrix where I have j22 minus j12 0 0, then I have here also 0, then I have minus j21 j11 minus j21 j11 j22 minus j12, into del u by del zeta, del u by del eta, del v by del zeta, and del v by del eta, isn't it? So we can solve it. So you see what will happen. If you have to find out the first term of the strain, how many terms are there? We have 3 terms in the strain matrix, right? So the first term of the strain matrix is del u by del x. So our first term of the matrix is epsilon xx, which is del u by del x. And how are we finding it? We are finding it by multiplying this with that, with this one, right? And of course we have determinant of j with us, and then we have j22 into del u by del zeta minus j12 del u by del eta, and nothing else, right? And aren't we getting the same thing from here? What are we getting? We are getting j here also. We are getting j22 into del u by del zeta minus j12 del u by del eta into, of course, determinant of j is there. So aren't we getting the same thing? So you see, this and this are same. So this term I should write here 1 by determinant of j, which is also here. Right? So it is just the arrangement of this Jacobian matrix so that we can deal with the four terms of the partial derivative in the local coordinate system. And this is how we can find out the strain matrix using this formulation. Okay. Now the term which we have to deal with is this. Okay, and this part is the A matrix. Okay, so this part is the A matrix, and now what do we have? We have strain tensor as A matrix. Shouldn't call it a strain tensor, I should call it strain matrix, is equal to A matrix into this matrix of partial derivative with the local coordinate system, and del v by del eta. But I need to further simplify this matrix also. How do I do it? I do it simply by using the relation that u is equal to n into d, right? So what will be del u by del zeta? That will be del n by del zeta into d. Okay, so this I should break, and if I break it, then I have A into a weird matrix which should tell me the value of, in terms of n1, n2, n3, and n4. So I should write it for the 4 shape functions. So I will have terms like, you see what I'm doing here. So I'm just writing this part, and then I will write that part at the end, and I'm writing this matrix using this relationship. So I have to find out del u by del zeta, for which I'm writing del n1 by del zeta, right? And I need nothing else, so this will be 0. And the second term is del u by del eta, so for that I should write del n1 by del eta and 0, and then I need nothing here, but I will need for del v's. So for that del v's I should write del n1 by del zeta and del n1 by del eta, right? This part of the total matrix is only for the shape function 1, and then you repeat it for shape function 2, 3, and 4. So that will be del n2 by del eta 0, 0, del n2 by del eta 0 0 del n2 by del zeta del n2 by del eta, right? And then you simply write it for shape function 3 del n3 by del zeta 0 0 0 0 del n3 by del zeta del n3 by del eta del n3 by del eta, and then you write it finally for shape function 4 by del zeta 0 0 0 0 del n4 by del zeta del n4 by del eta del n4 by del eta. This is my matrix, and then I write the D matrix, which is U1 V1 U2 V2 U3 V3 U4 V4, right? So what am I doing? I am just expanding this matrix in this form, okay, and A remains the same. So this matrix, let us call this matrix as G matrix, okay. So then I can write strain as A, G and D, right? And before we wrote strain matrix as B matrix into small d matrix. So this B matrix has been expanded in terms of A matrix and G matrix. What is A matrix? A matrix is simply the combination of the Jacobian, and G matrix is the partial derivative of the shape functions with respect to the local coordinate system, okay. So I hope this should be clear. All right, so now we have the strain formulation, and we can simply find out the stresses by using the D matrix, which we have seen in our one of the previous lectures, which simply defines the combination of elastic moduli and the Poisson's ratio. So basically it is if we write in a scalar form, stress is equal to elastic modulus into strain. So that elastic modulus is actually in the matrix form is D matrix. So sigma will be equal to D matrix into strain matrix. You see, we are not using the tensorial elemental values. So this is a little different. So this is why I call it matrix and not tensor. Okay, because I have told you that sigma also we don't write in 3/3 form. So sigma is equal to D into epsilon, and epsilon is basically B into D matrix. So this is how we will calculate stresses. And how do we calculate the stiffness matrix? That we have already discussed. So in 2 dimension we will have the thickness of the element, then we will have local integration of the B transpose D matrix B matrix into determinant of Jacobian into D zeta D eta. And in 3 dimension, well, we are not doing 3 dimension, but in 3 dimension we will not have thickness because we have 3 dimensions, and then we will have 3 integrations of B transpose D B determinant of Jacobian D zeta D eta and D psi. Okay, so we can calculate the stiffness matrix, and then we can also calculate the force, the body forces. So the body forces is simply the integration, so omega, so the body forces F are the integration of U transpose, which is our D matrix. So you can simply write D transpose F matrix, which is F matrix is the values at the node, so fx, xy, fy kind of things, into dv, and volume we can change at determinant of j d zeta d eta. Okay, so this is how we can find out the value of elemental forces. So basically it will be the thickness of the element into double integration, and then we will have nt determinant of Jacobian matrix d zeta d eta, and all this multiplied with the value of body forces in the x direction and y direction, right? How have we done it? Here the simple thing is that d we have changed as n into d. Okay, so instead you write u transpose, and u we have changed at nd, so u transpose will be n, it will be d transpose n transpose, right? So this is how this n transpose term comes there, and the n transpose term comes there, and we have f vector also. So f into d transpose gives us fx and fy, and then we have volume integration dv, which is broken in like this. So this is how we find out the forces. Okay, so from starting till end we have completed the formulation for a quadrilateral shape function. Now let us try to do an example. Let me see if we have time to do it. So let me just check if we have. Yeah, we have some time. Okay, so we will go as far as possible in this case. Okay, so we have the quadrilateral element, and let us say that the coordinate values, the global coordinate values, meaning x1, y1, x2, y2, x3, y3, and x4, y4, all those values. So those are 0, 0, then we have 2, 0, then we have 2, 1, and then we have 0 and 1. Okay, so this is the value of the coordinates, and let us say the value of d, meaning we have u1, v1, u2, v2, u3, v3. So let us say that those values are 0, 0, and then we have 0.002, then we have 0.003, then we have 0.006, then we have 0.0032, then we have 0 and 0. So this is, how many do we have? u1, v1, u2, u2, v2, u3, v3, u4, v4. Okay, so this is the displacement which we have, and let us say that the elastic modulus of this element is 200 gigapascals. So let us take our favorite value. Poisson's ratio is 0.3. Let us take that, and that's it. Now we will try to find out each and every term as we have described our problem. So first of all, we need to find out the value of the strain. In order to find out the value of strain, we need to find out B matrix into D matrix, and B matrix is A into G into D, so B matrix is A into G, so we need to find out A matrix and G matrix. So let us make A matrix first. What is my A matrix? So A matrix, no, this is not A. A is this. Okay, in order to find out A, I need to first find out Jacobian matrix, right? Then only I will have J11, J22, J21, J12. Okay, so what is my Jacobian matrix? Jacobian matrix I have to form as, so this is J inverse. So first I need to have J matrix, which is this. J matrix is del x by del zeta. del y by del zeta, del x by del eta, del y by del eta. Okay, so let us make first our, oh, it's a long thing. So instead of going to A first, let us find out the Jacobian matrix, which is del x by del zeta, del y by del zeta, del x by del eta, del y by del eta. Okay, this is what we have to find out. How do we find it out? We know the relation of x as n1 x1 plus n2 x2 plus n3 x3 plus n4 x4, right? Okay, so what will be the value of del x by del zeta? So first I have to write this whole thing in terms of n1 and x1 x2 x3 x4. x1 x2 x3 x4 I have, but we will do this in the end. So let me write out the save function. So save function ni is 1 plus epsilon, so zeta I eta I into 1 by 4. So n1 is 0.25 into, so what are the coordinates at node number 1? We have -1 -1. Node number 2 we have, so the zeta value is positive, so 1 -1. N3 we have 1 comma 1, and N4 we have zeta value is negative, eta value is positive, so -1. Okay, so what do I have? So first is 1 minus zeta into 1 minus eta. Then N2 I will have 1 plus zeta 1 minus eta. N3 I will have 1 plus zeta into 1 plus eta, and N4 I will have 1 minus zeta into 1 plus eta. Okay, so these are N1, N2, N3, N3s and N4s. Okay, well, so N1 is, so 1 by 4 I can take common. 1 by 4 will be everywhere, so let us take 1 by 4 common. Then I have, what do I have? I have 1 minus zeta into 1 minus eta into x1, right? So 1 minus zeta into 1 minus eta, but I have to find out the del x by del epsilon. Yeah, so that is what I'm doing. Okay, so this is into x1. Oh god. Okay, so okay, can I not hide the taskbar? Maybe I can see if I can hide the taskbar. So how do I hide it? I don't have any space in the taskbar to do anything. So lock the task. Okay, ouch, go now. Okay, so let us do this. X1 plus N2 is 1 plus zeta 1 minus eta x2 plus, and then I have what? Then I have N3. So 1 plus zeta 1 plus eta into, this is not going the task anyways. So 1 plus zeta 1 plus eta x3 plus I have N4 is 1 minus, so 1 minus zeta into 1 plus eta into x4. So this is my, so this is just n into x, and I have to still find out the partial derivative with respect to, so I have to write del by del zeta here. Okay, so what will be the first term? So the first term will have 1 into x1, that will go 0. Let me write 1 by 4 here. And then I will have minus zeta into x1, and partial derivative of that will be simply minus x1, right? Then I will have minus eta into x1 will become 0. Then I will have minus plus eta zeta x1. So that is plus, and eta will go away. So sorry, zeta will go away. So eta into x1. So this will be coming from the first term. Then from the second term, I will have, so 1 x2 will be 0. Eta into xt will be x2, and minus eta x2. Then I will have x3 plus eta x3. Then I will have then I will have minus x4 minus eta x4, right? This is del x by del epsilon. Okay, this is my del x by del epsilon. So this is my J11. So this is my J11. Okay, I know the value of etas, and I also know the eta and zeta, and I also know the values of x1, x2, x3 and x4. So we can actually really solve it here, but let us not do it. Let us make it more lengthy by finding out J12 also. So what is J12? Or instead, let us find out del x by del eta. Okay, so del x by del eta, for that I need to have x only, which I already have. So I just need to do the partial derivative with respect to eta. So what will happen in the first term? In the first term, I will have 1 x1 will go 0, and then I will have minus x1 and minus plus zeta x1. Then in the second one, I will have minus x2 and minus eta zeta. So it will be minus zeta x2. Then I will have zeta x3 plus zeta x3, and then I will have, so I will have zeta x4. So I will have x4 minus zeta x4. So this will be, this is what jx by j eta. So this is J21. So we have got J11, we have got J21. Similarly, we can find out J12. What is J12? J12 is del y by del zeta. Del y by del zeta. For this, we need to find out what is y. So y will be what? Y will be simply this, simply that, and we just have to replace x1 with y1, y2, y3, y4, right? So we don't need to do much. We simply can write this as J11 term where x's are replaced with y's. So J12 will be 1 by 4 into minus y1 plus eta y1 plus y2 minus eta y2 plus y3 plus eta y3 minus y4 minus eta y4, and j22 will be del y by del eta, which will be equal to 1 by 4 minus y1 plus zeta y1 minus y2 minus zeta y2 zeta y3 plus, oh, why do I have zeta y3 here? Here something is the problem. So this was del x by del eta, and for x3, so del x, so eta with respect to eta, so we will have only x3 here, not this one, x3 plus eta x3. Okay, so here we will have y3 plus eta y3 minus y4 minus eta y4. Okay, so we have zeta y4. So now we have all the components of the Jacobian matrix. Now we have to find out the A matrix, and A matrix has what? What do we have in the A matrix? What do we have in the A matrix? So where is A matrix? Is this one. Okay, so we need to put j22, j minus j12 and all those terms in this format. So here we need to actually really solve it. So we will have to solve it. We cannot just leave it in this complicated way. So let us put the values here. Okay, so we know the values of x1, x2, x3, x4, and zeta eta we have to put, and this will go in the limits when we do the integration. This will go in the limits when we do the integration from -1 to +1. So we cannot actually really solve it here. So let us keep j11, j21, j12, j22 like this, right? Let us keep it like this. Let us keep it like this, and J matrix is, have I done something wrong here? I don't think so, but I could have kept x's out of this, right? What did I do? I did del x by del zeta. So could have taken del x by del zeta, and x is equal to the shape function matrix into x. So I could have kept the matrix x out. Yeah, that also we could have done. Okay, so let us try it in a different way. So j, when I have to find out, I have to do del x by del zeta and del y by del zeta. Is it? So j12 is del y by del zeta. Okay, so this is del x by del eta, and here I have del x by del y by del zeta and del y by del eta. This is what I have to find out. So I can simply do what? I can write it as del n1 so, but then this will become a big matrix. Oh, but I can break it like this also. So I can simply, instead of not multiplying x1, x2s, x3s and x4s, I can simply write the terms which are there. Yeah, I can do that. So I can do that. So what I can do is, I can write it as 1 by 4 completely out of the matrix, and then I can write 2 into 1 minus eta plus 2 into 1 plus eta, and then minus 2 into 1 plus zeta plus 2 into 1 plus zeta and 1 plus eta minus 1 plus eta and 1 plus zeta plus 1 minus zeta, this whole thing into, so how many terms I have? I have two terms. And this should be, I have 2 by 2 matrix. I have 2 by 2 matrix, isn't it same? So J11, if I take x1s out, so I have minus 1 minus eta, so 1 minus eta, but minus 1 minus eta is going there, so 1 minus eta, and no, something is wrong here. So J I have to find out as del x by del zeta, right? I have to find out, just a second. Yeah, so what we can do is, let us look at this matrix here. Let us look at the components here, J11s and all. Let us look at J11. So J11, I can write it as 1 by 4, and then let us try to keep x1, x2s, x3s, x4s out. So then I can write it as minus 1 minus eta plus 1 minus eta. So here I will have x1, here I will have x2s, then 1 plus eta x3, and minus 1 plus eta x4, right? So this will be my J11, right? So what can I do? I can write it in terms of 4 components which are multiplied in the rows and columns ways. So I can write it as 1 minus eta, 1 minus eta, 1 plus eta, and minus 1 plus etas into x1, x2, x3, and x4. Can I do that? So this into x1, this into x2, this into x3, this into x4, right? So this will become, this is just the first component which I am getting. The second component I will get, so what is the second component? Is del y by del eta, which is J12. So here I will have to multiply with y1, y2, y3s and y4s, right? And what will be the component here? So I will have the component J12. Where is J12? J12 is going like that there. Okay. So in this case I have everything all right. J11s are good, J12s are good, J13s are good, and J14s are also good. Okay. So the point is, I have to integrate these values of epsilon and zeta at the end, and I cannot put the values right now. So I cannot actually find out the solution now. Okay. I cannot find out the solution now. But what I can do is, what can I do? I will have to write it in such a way. So then my Jacobian, I will not have J11s and all. So let us keep it this way without much botheration. Let us define our J11, J21, J12 and J22s like that. So J21 is 1 by 4, J21 is 1 by 4 into minus 1 minus zeta into x1, then 1 plus zeta into x2, then I have 1 plus zeta into x3, and I have 1 minus zeta into x4. This is my J21, and J12 is simply, do I not have the same thing like that? So I just have the same thing into y1, y2, y3, y4. So I have 1 minus eta plus 1 minus eta plus 1 minus 1 plus eta minus 1 plus eta, and y1, y2, y3 and y4. And J22 is simply J22 is simply this one, and instead of x's we have y, so we have 1 minus zeta minus 1 plus zeta plus 1 plus zeta and plus 1 minus zeta, y1, y2, y3 and y4, and this is my J22. So let us keep this in our hand. Let us keep this part in our hand, and from here we will continue in our next lecture. Okay, so